Alrighty, how about this first one here? How are we going to explain how this diagram plays out?
Do we have to talk about before it goes to the electric field?
No.
Okay. So the theta particles are negatively charged, so they turn up towards the positive side of the electric field.
Okay.
The gamma rays don't have a charge, so they just go through. And the alpha particles are positively charged, so they return to the negative side of the field. And then the theta particles turn more because they weigh less.
Okay. What what are we going to say for this radiation detector? What happens?
Something like the electron breaks apart and it goes through the circuit and gets counted and then comes back and reattaches to argon.
Sounds good. So that radiation comes in and knocks the electron off the argon. The electron runs to that wire in the middle because it's very high positive voltage. The electron runs through the circuitry, gets counted, comes back to the can where the argon with the plus charge is waiting for it. And then that argon with the plus charge and the electron reform themselves into regular old argon atom. And it can be used again. All right, we're 25 meters being exposed to that. We move back 15 meters and place 4 inches of lead in between me and what's my new exposure. My new exposure is, so we'll say intensity at 25 and at 40. So what do I mean by I-40 and I-25? That's the intensity I'd be receiving at 40 meters away and at 15 meters away. Why is it 40 meters away? Yeah, I'm 20 away and then I back up 15, so then I'm at 40.
It's not always one's on top.
Yeah.
Yeah.
Yeah, if we put the other one on top, then your answer is going to be upside down. So then on the other side, I'm going to put the distances, and it's because the larger the intensity number, the smaller the distance number, and vice versa. The further I get away, the less intensity I get. Then these numbers are flipped over. So then on this side, it's 25 squared meters and 40 squared meters. And so if I do that, oops, I'm not done. So then if I move that intensity 25 over to the other side, I'll get intensity at 40 meters is equal to 25 squared meters squared, 40 squared meters squared, times the intensity at 25, which was 120 millirem per hour. So I get 120 times 25 squared divided by 40 squared. And I get 46 point, I'll put 46.9 millirem per hour. So that meters cancel out, meter squared cancel out. Okay, so if there was no lead, then I'd be being exposed to 46.9. Does that number make sense? I mean, it went down. That's the most important part, right? And even though I only went back 15 meters, it went down a lot, right? Why did it go down so much, even though I didn't even go twice as far away? Because this square thing, so it's 25 squared, but then it's also 40 squared, so that 40 squared number is going up pretty fast. And so it's going to make the denominator number a lot larger. So I put 4 inches of lead, and since this is gamma radiation, the 10th thickness for lead is 2 inches. So I put 2 10 thicknesses of lead. So 2. So what do I do with a 10 thickness? So I just move this decimal place. I have to move it over 2 spots to make it 2 spots smaller, so I'm going to end up with getting 0.46. I guess I only have 2 sig figs, 0.47 millirem per hour. Okay. Do you guys have any questions about that one?
The 10 thickness thing, only for the gamma?
2 inches of lead is what it is for gamma, and there isn't a number for anything else. The only 2 things that we shield for are gammas and neutrons.
Okay.
And then the neutrons is 10 inches of water, lead, plastic, fuel oil, something. Not anything.
But those things. But for the gamma, it's 2 inches.
Of lead, yeah. So you can shield for neutrons with several different substances. The lead actually doesn't do anything to it, which is, we're still trying to figure that out. I put 10 inches of lead up, and the neutrons pretty much just go through it. Which you'd think because of its density, but whatever. Okay, did you guys have a definition for half-life?
How much time it takes for the mass of
So if I've got carbon-14, that carbon-14, it's going to turn into nitrogen-14 and a beta particle. So how long does it take that carbon-14 to turn into that stuff? The best answer that we have is, let's say I had 10 grams of it. It would take about 5,000 years for half of it to turn into nitrogen. That's what half-life is. So that means I've still got half of the radioactive stuff sitting there, but half of it's been turned into something else. And we'll talk about this a lot in class today. All right, this last one here. What do you need? That's what electricity is.
Transmitter,
What?
transmit electricity, like a,
You need a wire?
wire.
The actual definition would be a current carrying conductor or a wire. What else do you need? God, all weekend.
I put that, I don't know if it's right,
A magnetic field.
but I put that electrons being able to pass through material.
You need three things to make electricity. You need a wire, you need a magnetic field, and you need one more thing. What's the one more thing? This was the harder thing to remember or to understand. Relative motion between the two.
So would you just call that flow of electrons?
No,
No.
that's what electricity is. So how do I get the electricity? I need a wire. Oop, no, I messed up that one. Let's try this one. So, wire. And if this was, my hand was a horseshoe magnet, you okay with that? I have to do one of two things. I either have to do this, and electricity will be generated in the wire, or I can do this. I have to move the magnet, or I have to move the wire. One of those gets moved, and inside of the wire, the electrons start to move. That's electricity. So all a person needs to do is get something that's wire spinning and put a magnet around it. There isn't anything else to it. Okay.